Namaskar and welcome back to another lecture in our course on infrastructure asset management. We are in week 7 of this course and we are talking about maintenance of concrete structures. A basic introduction to this topic where we are talking about different aspects of maintenance of concrete structures from the point of view of infrastructure maintenance. The entire discussion is basically talking about maintenance of concrete structures in the framework that we are talking about in this course. This is a warning that I give you all the time that the material used in this course is strictly for academic and instructional use in this course and should not be used elsewhere. What you see on the screen is like the blackboard, and please make it a habit to make notes as usual using what is being projected and what is being stated. The course so far has overviewed the content including the conduct and concepts in infrastructure asset management. We have talked about schematic representations of deterioration and performance variations over time and the examination of the concept of service life and maintenance action in that framework. We have talked about case studies highlighting the role of different stakeholders in different phases of the project and the importance of a comprehensive strategy towards infrastructure asset management. We have talked about decision making frameworks including performance modeling considerations in budget allocation. In the present module, a mechanism based approach to chloride and carbonation induced corrosion has been discussed in the first 2 lectures in the framework of progressive deterioration and service life quantification. So, moving on the discussion today, which basically starts from these 2 graphs which we have often seen, the variation of deterioration over time and the variation of performance over time. This is something which we are familiar with from different modules that we have used. The discussion today talks about specifications which basically become a vehicle to provide the initial integrity to concrete. This initial value here in terms of performance is what we are talking about initial integrity. The concrete in the structure starts its performance journey from this point, and this point, whether it is here or it is here or it is here, this is governed by the specifications that we talk about, and that is what is going to be brought out through our discussion today. As far as this part is concerned, we have already talked about it and related this part to initial defects, and that is a matter which is pretty closely related to quality aspects, that is quality control during construction. So, of course, whether we start here or whether we start at 0, that is a moot question. The discussion today largely focuses on this part and its interpretation in more concrete terms as far as different mechanisms of deterioration is concerned. So, moving on, let us recall a few basic facts about concrete. It is a mixture of cement, sand, coarse aggregate, water and chemical and mineral admixtures. Sand and aggregate are inert fillers providing the bulk of the volume. In principle, nothing can be added to the concrete at a later date as a supplement. So, whatever we want to add in the concrete has to be added at the time of mixing, and it becomes an integral part of the concrete. At any later date, it is more or less impossible to add something to any kind of concrete. The ingredients and their proportions should be carefully chosen, therefore, keeping in mind the required properties of concrete and the environment in which the concrete is likely to be. Codes and specifications provide for the above through appropriate provisions, keeping in mind the likely deterioration mechanisms that a structure may be susceptible to, considering the environment and the materials. Now, this set of data has already been presented to you, and I think we have talked about it earlier, that this is basically an illustrative example of specifications for marine reinforced concrete structures. What is being done here is that the different zones of exposure have been defined and the maximum permissible water cement ratio has been defined for general construction and for concrete products. So, you can see that it ranges from 45 to 50 depending on different combinations, and apart from the maximum water cement ratio, we talk about minimum cover thickness for different structural elements depending on the same zones of exposure, and these values range from, let us say, 4 centimeters to about 7 centimeters. And I think I had given you this homework earlier and I am reiterating it once again. What are some of the other parameters that at times are used in codes for corrosion prone structures? Study some of these provisions from Indian and other codes for marine structures. This is just one example of how codes try to provide the initial integrity to the concrete that we use in a marine structure, and that is what is the starting point as far as this graph is concerned. So, if we change these water cement ratios, we will move either this way or this way. So, if we reduce the water cement ratio, we are going for richer concretes. What we can expect is that the initial level of integrity will be higher. Similarly, if we increase the water cement ratios, allow less strength in the concrete to be used and so on, then the initial levels of integrity are likely to move down. So, that is the kind of concept that we are talking about as far as our discussion today is concerned. Moving on, we have already talked about this slide, that in general we talk about these 4 mechanisms of deterioration: chloride induced corrosion, carbonation induced corrosion, cyclic exposure to freezing and thawing, and alkali aggregate reaction. And once we have the thought process to address some of these deterioration mechanisms, it is much easier to develop an appropriate mechanism for other deterioration mechanisms. Moving on, as far as iron and its corrosion is concerned, we have already talked about a diagram like this, that the steel bar is protected by an initial passivating film. This is the environment, this part is the cover concrete, this is the main concrete, and the effort is to be made to provide sufficient depth of this cover and the quality of this concrete to ensure that the steel bar remains protected during the service life of the structure. Now, as far as carbonation is concerned, we know that penetration of carbon dioxide from the atmosphere leads to an unstable passivating film, rendering this bar susceptible to corrosion. Similarly, in the case of chloride rich environment, when the chlorides move into the concrete or the cover concrete I should say, what happens is that this passivating film is damaged. So, in either case the surface here of the reinforcement is rendered susceptible to corrosion, and we have anodic and cathodic reactions that we have talked about, iron going to Fe2 plus, release of electrons, and the consumption of these electrons with oxygen and water to form hydroxyl ions. So, this is basically the corrosion reaction that we have talked about. This can be represented in a slightly different way, that as time goes on, the carbonated depth continues to increase, and we do not want this carbonation depth to reach very close to the reinforcing bar in the service life. And similarly, as far as chloride induced corrosion is concerned, we do not want more than critical chloride concentration in the neighborhood of the reinforcing bar as shown here. So, the idea is that the cover depth and the quality of concrete should be so determined that the bar is not compromised during the given service life of the structure. So, that is the thrust of having this point here. Moving on, we know that the chloride penetration in concrete is modeled as a diffusion process, and the diffusion coefficient here, that is D, is largely a function of the water cement ratio and the properties of concrete that we are talking about in this region, that is the cover concrete. That is what is given here as well, that the D represents the ease of diffusion. Of course, it is the diffusion coefficient in mathematical terms, but basically represents the ease of diffusion depending upon the porosity of the concrete mix, which in turn depends on the water cement ratio, the cement content and type, and other factors such as the level of saturation of the pores and so on. So, what is really shown here is a schematic of the concrete, that we have these coarse aggregates in mortar, and if we take a small part here, what we see is this HCP, that is hardened cement paste, and this is the pore structure. So, this pore structure could be coarse or fine depending on the kind of hydration that we have had, the strength of concrete and so on. So, moving forward, this diagram also we have talked about that research has shown that water cement ratio and the diffusion coefficient are related. Now, to what extent they are related is a different matter. For example, for a given water cement ratio, we find that there is a large range of observed diffusion coefficients. This is for blast furnace slag cements, this is the kind of variation that we have for ordinary Portland cement and so on. Having said that, the point that the water cement ratio basically is an important determinant, is an important factor on which the diffusion coefficient depends, and once we are able to figure out the diffusion coefficient, we will be able to find out how much time it takes for chlorides to build up at the level of the reinforcing bar. So, that is basically the thought process that we are talking about, and in order to provide initial integrity to the concrete, that is to the cover concrete, one of the important thrusts has to be the water cement ratio, and that is what is already given. So, the codes are aware, the people who wrote those codes, wrote those provisions, were aware of the fact that controlling water cement ratio is an important way of controlling the diffusion coefficient. Having said that, over a period of time, other methods such as those which are listed here have emerged as more direct measures of chloride permeability, and specifications are now beginning to prescribe these values directly as well, in addition to traditional provisions of water cement ratio, cement content and so on. So, what we will do today is basically just look quickly at some of these tests. Looking at the diffusion cell type experiments, basically a concrete block is taken here, and on one side we have a sodium chloride solution, pure water on the other side, and we have chlorides move in to this chamber from this chamber. So, this part here is an equation which represents how much flux will happen as chlorides move through this concrete. So, as far as provisions in the specifications are concerned, one can say that please carry out this test and the concrete will be acceptable if the concentration in pure water in, let us say, x days does not exceed so many ppm. Now, these numbers are the ones that are left open to people who are going to use the structure. So, for one structure we may have A and B as these numbers, for another structure C and D can be the numbers, and these numbers have to be decided by the owners and clients. So, basically what we are talking about is a test method which is given, and the specifications have to be drawn up separately. So, moving on, there is the rapid chloride permeability test, or the RCPT, which can be looked upon as an accelerated version of the diffusion cell setup that we just saw. Here too there is a concrete block, sodium chloride on one side, sodium hydroxide on the other, and conducting plates on the two faces connected to a 60 volt power supply. And what is done is the current that is flowing through this concrete is monitored, and the total charge that passes over a 6 hour period is what is measured, and that charge will be in coulombs. So basically this test method will give you coulombs, and what we are expected to interpret is that these coulombs are related to the diffusivity, and one can prescribe the kind of concrete that we need, and that is precisely what will determine our position on this graph. So if we want a very dense concrete, impervious concrete, the number of coulombs or the value that we have for coulombs should be very low, whereas under certain conditions, if we are willing to live with a slightly more porous concrete. Now more porous does not mean very porous concrete, but in that context, if we are willing to live with higher coulomb concretes, then we will move slightly lower as far as the initial performance is concerned. This chart here tells us how ASTM 1202 relates the coulombs to the diffusivity. So if we have more than 4000 coulombs, 2000 to 4000, 1000 to 2000, 100 to 1000 and less than 100. This is the kind of qualitative description of chloride diffusivity which is given as a guideline for interpreting the results obtained from the RCPT. And the last test that we talked about was the ponding test, where the concrete surface or a concrete slab is basically ponded with a chloride solution, and after a fixed amount of time we try to have a core and measure the chloride concentration in a slice at a fixed depth. Now obviously if this concrete was porous, then this concentration will be, let us say, high compared to a concrete which is impervious, and in that case the concentration under similar conditions would be much lower. So basically, as far as specifications are concerned, we can say that yes, you carry out this test and the concrete will be acceptable if the concentration at depth is equal to so much is not greater than some number. Now that is what is the challenge to people who are writing specifications. Test methods will give you values, and that is a central theme of maintaining good quality, high performance, that we have certain parameters, and based on those parameters we get values and we evaluate those values and have acceptance criteria. So that basically is the central theme that is running through our discussion today. So moving forward, we come to a different mechanism of deterioration, the cyclic freezing and thawing. We have talked about this mechanism earlier in this course. It basically involves disintegration of the pore structure upon exposure of the concrete to temperature variations across 0 degrees centigrade that cause pore water to cyclically freeze and thaw, leading to disintegration of pore structures due to the cycles of expansion in the pore water. So what we see here is scaling on the surface and pop out of aggregates. So basically what happens is that water present in these pores, that is the one that is cyclically freezing and thawing, leading to disintegration of pore walls and a situation which manifests itself in this manner. So if we have a concrete structure which is likely to be subjected to cyclic freezing and thawing, we know that, and therefore one of the things that we need to do to ensure initial integrity is to make sure that it has adequate resistance to freezing and thawing. Now as far as this resistance is concerned, it has been found that air entrained concrete performs better than non-air entrained concrete under these conditions. And this air entrainment means we need to measure the air in fresh concrete, and this is a simple air meter which can be used to measure the air content. Now that is something which in many engineering colleges we do not use, and that is something I think it is only a matter of time that the use of these air meters would become more widespread. Air entrainment requires chemical admixtures which are air entraining chemical admixtures, and these are commonly available. There is nothing wrong in using air admixtures, but they should be used with appropriate precautions. What happens is that once we do air entrainment, apart from the fact that concrete has more air content, it becomes more flowable and it also may reduce strength. Now, this is something which will become counterproductive. So, we have to be careful that if we are using air entraining agents, what are the steps that we are taking to ensure that strength is not getting compromised. Now, that is something which will come out only if we measure the air content, and that is why measurement of air content is a very important part of quality control and ensuring initial integrity as far as the concrete is concerned. Now, depending on the size of the aggregate, the air content in non-air entrained concretes could be about 1 to 2%, and in cases when concrete is subjected to freezing and thawing, then specifications often require 4 to 6% of air. Now, that requires appropriate changes in the mix proportions, and that is something which concrete engineers routinely can do. As a related concept, we come to durability factor and air content. Now, if we change the air content in concrete and we try to plot what is called the durability factor, and what this durability factor is something which I am leaving it to you to do as a homework. Having said that, the durability factor in the range of air content of about 2.5 to 3% is practically 0. It becomes very close to 80 or 90 the moment we have air content in this range, that is, let us say 3.5 to 4.5, 5%. Beyond this point, the air content does not affect the durability factor, and beyond this point again the durability factor tends to drop. So, now this is where we need to understand that how much air content should we have in the concrete. So, the best thing to do would be to operate in this kind of a region and not go beyond this, because in this region we are not getting any benefit. The durability factor is still very high. The durability factor has already reached a certain level, and the benefit of increasing the air content is practically 0. Now, as far as the measurement of durability factor is concerned and the performance of concrete as far as air entrainment and freezing and thawing is concerned, one of the important parameters that we measure or we need to measure is the dynamic modulus of elasticity. I request you to go through ASTM and other standards which tell you how these tests are to be carried out. What is shown here is a chamber where concrete specimens are exposed to cyclic freezing and thawing under standard conditions. So, as far as this chamber is concerned, the cycles can be defined in terms of the temperature and the time. How much time at this temperature, how much time at this temperature, and what cycle, so that we can monitor the changes in the properties of this concrete in this prism, which is typically 100 by 100 by 400 millimeters. How does the properties of this kind of a prism change as it is exposed to more and more cycles of freezing and thawing, and that is done through the measurement of dynamic modulus of elasticity, which is shown in this picture. Depending upon the relative orientation of the sensors on this specimen which are placed on the surface, the measurements can be made for longitudinal, torsional or transverse vibrations, and we get an estimate of the dynamic modulus of elasticity. So, how we interpret this result is what is given here, that we have the dynamic modulus of elasticity plotted versus the number of plotted against the number of cycles. So, as more and more deterioration happens, the dynamic modulus of elasticity tends to go down. And now, what is the behavior of this graph is determined by factors such as the strength, water cement ratio, type, and the air content, that is the air entrainment in that concrete. So, if we are able to fix a critical limit of the modulus of elasticity, then we can talk in terms of a specification which could be written as the concrete used shall be such that when tested in accordance with the method which is given here, a certain number of cycles, a maximum temperature, a minimum temperature, the different durations and so on, if that cycle and so on is fixed, then tested according to that method, the reduction in ED shall not be more than some x% at the end of n cycles. Now, that is how the specifications will be written to ensure that the initial level of performance of my concrete is here and not here or here. And obviously, parameters such as the number of cycles or the extent of reduction acceptable can be varied in a specification from structure to structure depending on its importance, location and so on. We must understand that as far as, let us say, a country like India or any country is concerned, the freezing and thawing cycles that a structure may go through is not the same for all the structures. So, depending on its location, depending on its importance, we can have different values of x and different values of cycles. So, that is how we can work as far as writing specifications is concerned when we expect the concrete to be exposed to cyclic freezing and thawing. Moving on, we go to another mechanism which is alkali aggregate reaction. Now, usually aggregates in concrete, whether it is sand or its coarse aggregate, they are inert and do not react chemically with the pore solution. Exception is alkali aggregate reaction, where the presence of certain minerals in aggregates, whether it is sand or its coarse aggregate, renders them reactive. And this reaction is very slow and causes deleterious expansion in concrete. This reaction is between these minerals, which is called reactive silica, and the alkali ions from the cement. As far as alkali aggregate reactions in concrete is concerned, there are two prime players or factors. One, what is needed is characterization of aggregates to ensure that minerals which are reactive are not present, or if they are present, then one should be aware of that when choosing the quarry. And the other player is the alkali content in the cement that we use. So, if with these two we can more or less control the occurrence of alkali aggregate reaction in a given concrete. Apart from that, of course, there are environmental factors. It is very important to note that alkali aggregate reaction and the deleterious expansion happens only when water is absorbed by the products of the alkali aggregate reaction. I am not going into the details of this part, because at the end of it, this is not a technical discussion on alkali aggregate reaction or the durability of concrete, but basically an introduction to the problem from a purely management perspective, and choosing the right kind of tests to be carried out to identify the material that is used in the concrete, so that to begin with the concrete has the kind of integrity that we want. So, moving on, as far as the expansion is concerned, this is a schematic representation of how the expansion moves as far as months is concerned. Now, this obviously is in a very controlled environment and accelerated tests. You can see that the expansion could be as much as about 0.09%, it could even exceed 0.1% at times, and this expansion and reaction is related to several factors. This could be related to alkalis present. Now, that means it is related to the cement alkali content and the cement content. So, if we have a certain alkali content in the cement and we use a certain amount of cement in the concrete, that is what is giving us a certain amount of alkali in the concrete. Then it depends on how much reactive silica is present. It depends on the surface area which is available. So, coarse aggregates have less surface area compared to the same mass with finer aggregates. So, if we have a certain amount of alkalis present in the system, the concentration here in terms of alkalis per surface area is much higher here than here. So, that would determine the intensity of the alkali aggregate attack. That is what we are talking about here, that is the particle size distribution of reactive particles. And of course, the reactivity of the mineral and environmental conditions such as temperature and humidity. So, all this together would control and determine the reaction and the expansion. I am leaving it to you to find out what is 0.1% expansion in terms of microstrains, because some of us are more trained to think in terms of microstrains and try to relate that number with the stress strain curve of concrete or steel, and then you will realize what is the import of something like 0.1% expansion on account of alkali aggregate reaction. Moving on, what does alkali aggregate reaction lead to? It leads to additional strains in the reinforcing steel. Basically what is happening is that if we have a steel bar here surrounded by reactive concrete, that is concrete where alkali aggregate reaction is going on, and this concrete wants to expand. Now, this amount of expansion has to reflect in the reinforcing steel as well. In fact, the amount of expansion that we can have in free concrete will probably be more than in reinforced concrete. That said, in the case of reinforced concrete, there will be additional strains, additional because these strains would be tensile, and steel bars in concrete are often in tension. So, that is what we are talking about when we say additional tensile strains in reinforcing steel on account of alkali aggregate reaction. It leads to cracking in surface concrete that could promote ingress of other deleterious materials such as carbon dioxide deeper into concrete, map cracking that reduces the modulus of elasticity of concrete, and also its compressive strength besides being aesthetically unacceptable. Now, the first step therefore in handling alkali aggregate reaction is to identify reactive aggregates, and that is the first job when we start a major construction project. Go to the quarry, try to get the aggregate and identify or establish whether the aggregates from that quarry are reactive or not. Common tests which are used to establish the reactivity of aggregates include petrographic examination, quick chemical test, a mortar bar expansion test, and so on. And these are standard methods that need special attention, and it is not in our scope here to go into the details of those tests. Having said that, what I will do is just briefly talk about these two tests to give you a flavor of what these tests actually involve or how they are supposed to be interpreted. Coming to the quick chemical test, what we do is dissolve a certain amount of aggregate with a certain particle size distribution in sodium hydroxide at a certain temperature for a certain period of time, and then try to see what is the reduction in alkalinity and what is the amount of dissolved silica. Based on these two, we try to plot this graph and divide the region into innocuous and non-innocuous, that is deleterious or harmful region. So, if we find an aggregate in this portion, it is deleterious, here it is innocuous. If we examine the results of these tests more closely, we find that actually codes tell us to interpret it in three parts: innocuous, potentially deleterious and deleterious. So, if we are in this region, it is actually deleterious, this is safe. This region here, the test is actually inconclusive, and in this part it is often recommended that other tests such as the mortar bar test is carried out. So, that is so much as the quick chemical test is concerned. As far as the mortar bar expansion test is concerned, what we do is use these kind of specially designed molds with a very specially designed bolt like this, and use a comparator here to plot a graph which is something like this. We try to plot the expansion observed over a period of time, and we get a graph which can be schematically shown the way it is drawn here. We have a maximum expansion, and there are times, that is incubation, initiation, rapid expansion and tapering off. Depending on the type of reactive mineral, they show different characteristics. Now, this mortar bar expansion test obviously is carried out under standard conditions. That is, here too the mortar which is used is a standard mortar. That is, we use the aggregate which is supposed to be used, but in order to accelerate the test to give some meaningful results within reasonable time frame, the alkali content is often augmented by using artificial alkali. It is not only the cement which is used, it is not only the cement that will be used in the quantity that it is used, but also augmented alkali. Similarly, the aggregate is ground to a certain size, and therefore, this mortar is not really the concrete that is used in the actual structure. So, what is being done here is that we are using this test, which is basically being carried out using a mortar bar to decide whether the concrete that we have in the structure is going to be susceptible to alkali aggregate reaction related expansion or not. Now, we can have limits on the maximum permissible expansion, the kind of expansion which we get at a certain point in time, and so on and so forth. Much like the kind of discussion that we had when we are talking about the modulus of elasticity or the dynamic modulus of elasticity. How much reduction do we allow in a certain number of cycles? Similarly, depending on the importance and so on, we can talk in terms of the maximum expansion that will be allowed over a certain time period of the test. Here again, the thread is the same. Tests give results and specifications provide the acceptance criteria depending on various factors. What I am leaving to you to find out is the basis for interpretation, and the acceptance criteria may be in Indian and other codes relating to concrete construction. So, this is the story as far as the aggregates are concerned. So, using the quick chemical test or the mortar bar test, we determine whether the aggregates are reactive or not. Now, coming to the cement side of the equation. Cement comprises oxides of calcium, silicon, aluminum and iron, and therefore, OPC, that is ordinary Portland cement, is also made up of compounds of these oxides, and the chemical composition of the cement is given in terms of these oxides, and a typical percentage is shown here. Now, what is shown here, what is relevant from the alkali aggregate reaction point of view is this row here. That is the one that is alkali. Alkali in this case is not so much the hydroxyl ions, but the sodium and potassium, that is the alkali metals. Now, these alkali metals are present in cement as impurities and find their way into the cement through the manufacturing process. Now, the total alkali content of a cement is expressed in terms of equivalent Na2O, which is given as the Na2O plus 0.658 times K2O, and this 0.658 comes from the relative atomic weights of sodium and potassium. So, in this case, for example, the equivalent Na2O will be 0.6 plus 0.66, let us say, times 0.4, whatever that number turns out to be, that will be the equivalent Na2O content of this cement. So, obviously, based on this equivalent Na2O content, The cements can be classified as low, normal or high alkali. Obviously, in a situation where the aggregate is likely to be reactive, it is not possible to change the quarry. The option is to use low alkali cements. Now, low alkali cements would mean those cements where the presence of alkali metals as impurities was lower. Now, that is how we try to mitigate the problem of alkali aggregate reaction. So, moving on, prevention and control of alkali aggregate reaction basically involves use of non-reactive aggregates, mixing reactive and non-reactive aggregates. If it is not possible to avoid reactive aggregates altogether, try to see if we can replace parts of it and still use some reactive aggregates, control the alkali content in the concrete, which could involve use of low alkali cement or the use of supplementary cementitious materials. So, basically what is being said is that if, for example, normally we expect to use or we want to use 400 kgs per cubic meter of cement, and this cement has 1% of alkali. Now, the total alkali content in that concrete, because the cement is 400 kgs per cubic meter and it contains 1% of alkali, the total content of alkali in this concrete can be calculated. We can control this by saying that okay, instead of 400 kgs of cement, we will use 300 kgs of cement or 250 kgs of cement, and the rest will be replaced by some kind of supplementary cementitious material. It could be fly ash, it could be slag and so on. So, this basically reduces the total amount of alkali in the system, that is concrete. So, that is one of the ways of addressing the problem of alkali aggregate reaction. Controlling the cement content, of course, that is one way, that instead of 400 you work with 300 or 250 kgs of cement itself, and of course preventing the structure from coming in contact with water. Now, this is something which I have not discussed in great detail. I think we will skip this detail for a separate discussion. It has been included here only for the sake of completeness. Now, with this we come to an end of our discussion today, where through examples of measurement of diffusivity, measurement of the dynamic modulus of elasticity, and our discussion on aggregate reactivity, along with our discussion on the alkali content in cement, we have tried to give you an insight into how we try to get the initial integrity of a concrete. Now, whether we are talking of the cover concrete here or we are talking of the main concrete, typically it is the same concrete which is used. It is very rare to find a situation where the cover concrete is a different concrete and we have a more dense concrete in the cover and so on. That is something which is very, very special. So, basically what we have tried to do is to say that okay, if our specifications talk in terms of different quantitative parameters, different tests, different acceptance criteria for the concrete, in addition to traditional ones like water cement ratio, cement content, strength and so on, we will probably be able to ensure better initial performance, and that will go a long way when it comes to ensuring higher service lives or ensuring that for a given service life what is the kind of concrete that we need to have to begin with. And with that, here is a list of references which will probably help you understand the kind of discussion that we have had today. And as usual, I would like to thank all my teachers, students and colleagues who have helped me understand the subject better. Thank you.